In this video, I'll introduce the mathematical models that go with electric current and direct current circuits. So first, we have a definition of current. So current, I, is, we've seen this before, Q, that's charge, per time. So current is a measure of how much charge passes a certain point in a certain amount of time. Next we have Ohm's law. Ohm's law says that the voltage across a component in a circuit is equal to the current flowing through that component times the resistance of that component. So V equals IR. Ohm's law is a bit like Hooke's law. If you remember Hooke's law, that deals with forces and springs, and it says that the force generated by a spring is proportional to the amount that the string has been stretched. And it's only true for some materials. For an ideal spring, it's fine. For a rubber band, it doesn't work. Ohm's law is similar. For most metals, Ohm's law is valid. But for something like a light bulb, Ohm's law does not work very well. Next we have resistance. So this resistance R is equal to the resistivity of the material times the length of the material divided by the area of the material. Then we have power in an electric circuit. So the power is equal to the current times the voltage. If you want to look at a single object within the circuit, it's the current flowing through that particular component times the voltage drop across that particular component. Using Ohm's law, V equals IR, you can see here, if you replace this V with I times R, you would get I times R, or I squared R. So both of these are just different versions of this IV version. The power is measured in watts. Kirchhoff's rules, the loop rule says if you start at a certain point in a circuit and make a complete loop and come back to that same point, you'll find that the change in voltage from your starting point to your ending point is zero. The junction rule, a junction is any place where two wires or other conductors join together within a circuit, and within any junction, the amount of current going into that junction has to be equal to the current coming out of the junction. You can't pile up charge at a junction. I mentioned series and parallel. We'll look at equivalent resistance and equivalent capacitance when resistors are in series or parallel, and when capacitors are in series or parallel. We'll look at this in more detail later.